physics research operated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
And welcome to Jefferson Lab's Science Series Public Lectures. My name is Scott Price. I'm a staff scientist here at Jefferson Lab. I work with the polarized electron source group, and we work primarily in the injector, the portion of the accelerator where the electrons start their voyage at 100 kilovolts electron energy and go to 4 GeV, 4 billion electron volts in the experimental halls. My primary responsibility is to commission a 5 MeV Mott scattering polarimeter, which measures the beam polarization in the injector. Tonight's lecture is on fusion. Our speaker tonight is Dr. Andrew Post-Zwicker of the Princeton Plasma Physics Lab. He's currently senior program leader of the science education program there. Dr. Post-Zwicker's primary research interest is plasma physics. He was awarded a PhD from Johns Hopkins University in 1992. But he is also interested in teaching physics topics as well. He has taught junior high and high school teachers how to present contemporary physics subjects to their students. He has designed and taught a course for middle school science teachers on energy and the environment, and has taught summer enrichment science courses to exceptional high school students. Most recently, he has used World Wide Web sites to teach undergraduate and pre-college science courses. You can even visit one of his websites and interactively run a virtual plasma fusion reactor. Dr. Post-Zwicker has received awards for his work and was recently featured in a PBS documentary on the use of the internet in the classroom. Please welcome with me, Dr. Andrew Post-Zwicker.
Hi, thanks for coming out. Glad to see everybody here. We're going to spend about an hour talking about fusion and energy and the 21st century. And I call my talk, can you see that in the back? And today's lecture is going to be, oh, I can really hear myself. Today's lecture is going to be a little bit different, and I'm going to take a bit of a risk myself, in that you heard that I do a lot of interactive work on the World Wide Web, and I teach in a very interactive way. And this is going to be an interactive lecture. And what I mean by that is this. Here's one of the only graphs I'm going to show tonight. This is the attention curve. Typical attention curve, it holds for any age. And I see we have a variety of ages here. And the x-axis right here, this is time. And this just assumes about a 40-minute lecture. And this is your attention from 0 to 100%. Okay? Now what you can see is that right about now, I've been talking for about 30 seconds. And I've got about 3/4 of the people in this room, I have your attention. And if I talk for a few more minutes, I'm going to get pretty close to 100%. And then after about 10 minutes, we're all going to zone out. And I do the same thing. So, and then what happens right here? Well, if you're in school, the teacher says, okay, let's talk about the homework. If you're at a lecture, oftentimes someone will say, let's put up the conclusions. And of course, this isn't always true. I've seen absolutely brilliant lectures by brilliant lecturers. But it's difficult to keep your attention going for a full 40, or in this case, it'll be about 50 minutes. So here's what we're going to do. And this is a bit of a risk because I see a variety of ages, a variety of grade levels. I'm going to talk for about 10 minutes at most at a time. And then we're going to stop, and I'm going to put a question up. And it's a multiple choice question. There's no mathematics. And I think that regardless of what grade you're in, you'll be able to try and answer. You have about a minute, and then I'm going to ask for a show of hands, A, B, C, or D. And we'll take a little poll. Then Look around when you raise your hand and who else is raising their hand at the different answers, because I'm going to give you 2 minutes to convince your closest neighbor that you're correct. Okay? And that could be your mom, could be your brother, could be a classmate. And then I'm going to poll again. And if I've asked the questions well and the answers well, what we'll see is that you will teach yourselves the different concepts, because by talking with each other, things that perhaps weren't clear in your head or I didn't even explain very clearly will start to become more clear. I've got 4 questions. They won't be very painful. There's no grades on this. We're set. So I'm going to talk about energy. I'm going to talk about fusion energy. And to begin, I'm going to show you the closest fusion energy reactor to us right now. And it looks like this. And it's our sun. Can we dim the lights at all? And is this pretty hard to see? I don't know if this helps at all. Okay. Well, the sun is the closest fusion energy reactor to the Earth. The sun and all the stars are powered by fusion energy. And the reason why I call my talk Creating a Star on Earth is because what we're trying to do is mimic the power source for the sun here on Earth. But before we talk about fusion at all, we have to talk about energy. And why would we possibly care about making a new energy source? What's going on with the energy we use, fossil fuels? You hear a lot in the news about greenhouse gases, global warming, and things like that. First of all, what you have is that our population is increasing every year. And in the next about 40 years, our population is expected to perhaps as much as double. And at the same time, the energy use, which is just supposed to be represented by the size of this circle, is supposed to triple over the next 40 years. And I've put up here what we have in terms of the breakdown, at least in 1995. Thermal is the fossil fuels, so about 2/3 of our energy is produced by fossil fuels. Hydroelectric, nuclear, which means fission in this case. Geothermal makes up barely a fraction. Other, which would include solar, is also just a very insignificant fraction right now. So we have more and more people who are using more and more energy. And this isn't one of my questions, but which country do you think uses the most energy per person? Yeah. See, that wasn't a difficult question. We are the biggest wasters of energy in the entire planet. First of all, in terms of what's going on in the world, 8 billion tons of oil equivalent is what's consumed every single year. And the average, which this is called kilowatt hours per person, it's just a measure of energy. The world, on average, uses 2,000 of these units. And you can see that the United States, on average, we use 12,000. Each single one of us in this room, I'm no better than anyone else in terms of using energy, driving our cars, leaving our lights on at night, our coffee makers that have little clocks that are flashing all the time, our VCRs that are flashing. And you see that's more than 5 times what the world's average is. And here's Japan and Great Britain. And China and India, you can see their numbers are rather small. But remember that China and India have huge populations. China's somewhere over 1 billion. India is around 1 billion people. So although they don't use much per person, the total amount of energy they're using as a country is quite large. And China in particular is increasing their technology very rapidly. And so the amount of energy that they're going to use over the next years and decades is increasing tremendously. So anybody know where the electricity, what the fuels for electricity in this room right now? I have no idea. Any ideas?
Probably nuclear.
Is it nuclear? Is there a nuclear power plant close by? Okay. Up in Princeton, most of ours is coming from, I believe we have a coal plant as our closest one, coal power plant. So when we talk about fossil fuels, we're talking about coal, oil, and natural gas. And problems with them are that, first of all, they're going to run out. Even coal, which there's quite a bit of, is going to run out. And they're very dirty. Coal in particular, though we have a lot of it, can put out a tremendous amount of pollution. Oil, we use oil for gasoline in our transportation. We can move them, but also we have a problem with the finite supply and the air pollution. And natural gas, we have also problems with those as well. No matter how much we say we have, and I'm not going to give an estimate of how many years we have left, because that's very speculative, but it's a finite supply. I mean, eventually we are going to run out of our fossil fuels. And the amount of greenhouse gases and its effect on the Earth and the entire climate of the Earth is increasing significantly. The alternatives to the fossil fuels are fission. Fission works. It's powering electricity right here. But the waste is a huge problem. Nobody wants the waste from a fission power plant in their backyard. Hydro, which is creating a dam, is clean. There's no pollution in terms of the greenhouse gases, and carbon dioxide, CO2, is the predominant greenhouse gas. But you've got to make a dam. You've got to destroy habitat, and there's not rivers everywhere, so that hydro is not necessarily a great energy source for any place you want to be geographically. Wind is the same thing. You've got to have wind, and you've got to be able to store the energy for wind. Geothermal, you've got to be able to dig down. And solar, you've got to have a lot of sunlight. It's not going to work perhaps so well in a place like Seattle, which has a lot of clouds and rainy days. So before we talk about fusion, I'm going to ask the first question. So we'll put you on the spot right now. And although those who are so inclined could try to do the math, the idea is for any of these questions is not to try to do the math, but just think about the concept and answer what makes sense. So here's the question. I said every 40 years, roughly the way we're going, the Earth's population is going to double if we keep the same rate. And this is an exponential growth is what I'm getting at. This is like if you tell two friends something, who tell two friends, who tell two friends, who tell two friends. Hope you can read this in the back. And we have 6 billion people on the planet right now. And I'm saying if it takes 40 years for the population to double, what percentage do we need to have every single year? 2% a year, 10% a year, 20% a year, or 50% a year increase in our population for the world so that in 40 years, the entire world's population will double. So take a minute, think about it, and then I'll ask for a show of hands. Okay. How many people, by a show of hands, say it's 2% a year? All right. 10% a year? 20% a year? And 50% a year? Okay. If there was someone near you who had a different answer, convince them that you're right. I'll give you another minute or two for that. Okay, let's poll the audience one more time. 2% a year? A lot more hands went up. 10% a year? What did I say, 20% a year? And 50% a year. It's 2% a year is the right answer. So think about that for a second. It means that if for every 100 people in 1 year, you only need 102. And you need that to happen every single year for 40 years, and you double your population. And that'd be true of people, it's true of bacteria. It's called exponential growth. So it doesn't take a very large population increase in a single year, but if it happens every single year, our population increases rapidly. Okay, so let's talk about fusion. And why, for the last 40 years, 40 plus years, we have throughout the world been studying fusion as this mecca of energy, unlimited clean energy. Why is it something that's captivated the world's scientists? One thing is that it's abundant. It comes from water. The way we're going to do it on Earth is we're going to take, in this case, deuterium, which is also sometimes known as heavy water, or it's an isotope of water, of hydrogen, excuse me, and we're going to burn it, cause it to fuse, and turn into helium. And the Earth is more than 2/3 covered with water, so our fuel supply is predominantly coming from water. There's no nuclear. It is a nuclear process, but a nuclear accident, unlike a fission power plant, is impossible. There are no greenhouse gas emissions. It's not a 100% clean power supply. There is some nuclear waste, but it's not like a fission power plant again, where your waste is going to last tens upon thousands of years. And there are no direct weapons applications. And it's very, very powerful. It's an extremely energetic reaction. It's so energetic that if you could take the top 2 inches of Lake Erie and take the fuel there, that by itself is equal to, what is this, 1.6 times the known world oil reserves. Just take the top of, it's a big lake, but still it's not much in terms of the total amount of water on the planet. So it's a tremendously energetic reaction. Another way to look at it and compare it is, what if you had a fusion power plant now? Well, we could look at how much fuel in a single year a power plant needs. And so a 1,000 megawatt power plant is kind of typical. And if you had coal, if you wanted to power this power plant for a year, you need 2.5 million tons of coal. And it would take you approximately 250 trains coming in, 100 cars each, to get all of that coal to your power plant. You could do oil. Same thing, you need 11 million barrels of oil, or 11 super tankers, each bringing in 1 million barrels of oil each to power this. For fission, you're doing a little bit better. You need 28 tons of uranium dioxide, and so you're going to need 1.5 railroad car loads to bring that in. But for the same thing for fusion, you need a pickup truck. It's a half ton of fuel. So you can see that you don't need much, which is another reason why it would be such an unlimited source of energy. You bring all that in, the equivalent of all these super tankers and trains, in a pickup truck. So how come? Why is fusion such a powerful reaction? Well, what fusion is not, it's not chemical combustion. When you burn something, burn a piece of paper or burn anything. Chemical combustion, what you're doing is you're rearranging the atoms. So in this case, your fuel, which would be on the left side, could be methane and oxygen. And you put them into a reactor here. And what you would get is carbon dioxide and water, but you've rearranged the atoms. Methane is carbon and 4 hydrogen. The yellow is carbon, and here are the red are the little hydrogen. You've moved atoms around. And when you do that, you can release energy, but not very much. It's something we measure electron volts, and you get a few of them for every combustion reaction. Fusion is much different than that, because in fusion what you're doing is you're rearranging the protons and the neutrons in the fuel. And what I'm going to talk about always for what we'll do on Earth is deuterium, or when it's a nuclei, it's called the deuteron, and a triton, which is tritium. And what these are hydrogen with an extra neutron. So deuterium, or the deuteron, is a proton right here, that's the plus charge, with a neutron, which has no charge. The tritium nuclei, the triton, has the proton with the 2 neutrons here. Regular hydrogen just has the plus charge, just the proton. If you burn these in a reactor, you rearrange your protons and neutrons. What you get out is helium nucleus, which we call an alpha particle, and an extra neutron. And you can see each one of these reactions, instead of a few electron volts of energy, you get 17.6 million electron volts. So it's millions of times more energetic per reaction. And there's a really strange thing going on with this nuclear reaction. And involves perhaps the most famous equation in physics, E equals mc squared. But if you could take your deuterium and your tritium and put it on a scale to measure its mass, and you could put the helium and the neutron on the other side of your balance, you'd find that the deuterium and the tritium weigh more. And remember, you're just rearranging the protons and the neutrons. And so what you've happened is that you had a change of your mass and produced a tremendous amount of energy. And you see, here's another statistic. 1 gram of deuterium tritium fuel, just 1 little gram, is the equivalent of about 2,400 gallons of oil. So to see if what I just said makes sense, I'm going to put up another question. Okay. So what I just said, during a fusion reaction, the reactants, the deuterium and the tritium, have more mass than the products, which is the helium and an extra neutron. The total number of protons and neutrons before the reaction is the same as the total number of protons and neutrons after the reaction. Yet the total, but what did I say here? Oh, I just got confused. Sorry. I mean, the total number of before is the total number. Why is that? Does this question make any sense? I wrote this morning. Does it make sense? Am I just getting confused? Okay, there's the question. I won't try to look at it. What's going on? Okay? Oh, that's right. It makes sense. Where's the mass? That's the question. Sorry about that. Why is it that if the total number of protons and neutrons are the same, yet when you put them on, if you could put them on a balance, they don't weigh the same amount? By rearranging them, something happened with the mass. How come? Some of the mass is broken away during the reaction. The fusion reaction consumes some of the mass. The mass is found in the velocity of the products, the fact that they're moving away quickly. Or the mass of a neutron or a proton is not a constant. It could change. So I'll give you a minute and think about one of those 4 answers. Okay. What's going on? Answer A. Some of the mass is broken away during the fusion reaction. Okay. The fusion reaction consumes some of the mass. Okay. The lost mass is found in the velocity of the products. Okay. And the mass of a neutron or a proton is not always constant. No, I did pretty good. We had a nice even spread. Okay. There's a lot of people, a lot of different answers. So I'll give you 2 minutes. Find someone who doesn't agree with you and convince them that you're right. second. Okay, let's take another poll. Answer A, some of the mass is broken away during the fusion reaction. Okay. B, the fusion reaction consumes some of the mass. All right. C, the lost mass is found in the velocity of the products. All right. And D, the mass of a neutron or a proton is not always constant. Okay. Now, this is a tough one. This is C. Lost mass is found in the velocity of the products. What that means, put this back for a second. Energy equals mass times the speed of light squared. Mass changed, so energy, that's where the energy came from. And what happens is that energy is kinetic energy. And so it's how fast the particles, the helium, the neutron come out, and they come out extremely fast. So that excess mass is actually found in their energy, their kinetic energy. Okay, let's keep on going. So we know that fusion is a very energetic reaction, but how are we going to get it to happen in the laboratory? How does it happen in the stars? How does it happen anywhere? Well, first of all, remember there's a proton, there's a positively charged proton, both for the deuterium, the deuteron, and for the triton, the tritium. Okay? So they're both positive, which means they repel each other. Like charges repel. So what you have to do is you have to have a way to get them close enough together, because it turns out that if you can get them close enough together, they actually become attractive and fuse together. And that has to do with what's called the strong force. To do that, we heat the fuel. And we heat the fuel until they have enough energy, enough kinetic energy, that they will collide and overcome this repulsion. And we actually have to heat the fuel to above 100 million degrees. And we do this in the laboratory. At this temperature, atoms are torn apart if they collide. The electrons are stripped away. The electrons in the nuclei, or we call these ions, move independently, and what we have is something called a plasma. And I work at the Princeton Plasma Physics Laboratory. And plasmas are very common. They're not so common on Earth, but they make up, some people say, as much as 99% of the universe. Where we find them, sorry about the yellow not coming out so well, naturally flames and lightning and the aurora, the northern lights, or stars are all plasmas. What we create, fluorescent lights, neon signs, are plasmas. Some of our welding in furnaces, this is arc furnace that says, some of our power switches for very high power applications, and the entire semiconductor chip manufacturing process is plasma processing. All the computers, the CPUs for the computers, those chips are made by plasmas. So let me show you a couple of things. First of all, what I said, here's a little demo of fusion. I guess I'll do it in the center here. Like charges repel. And this is done with magnets. I don't have fusion right here because this is definitely not 100 million degrees. But you see, like charges repel. But if you have a way to get the deuterium and the tritium close enough together, and in this case I'm going to use pressure to squeeze the top one together, get it close enough together, they attract. Think about that's kind of strange, because if you do that with two normal magnets, they'll never attract. Okay, I'll just do it one more time for people to see. And for those who are wondering how it's happening, there's no moving parts. There's no magnet inside here flipping. And a further challenge, I've had one person, whenever I've done this before, actually figure it out. And I've asked people from professional scientists to students. It's not very intuitive what's going on here. But you can see, normally they repel, but if you could somehow get them close enough together, they attract. The other thing is I brought a plasma with me. Normally I can often point up to the fluorescent light bulbs, but in this case, what I have is a small fluorescent light bulb. And hopefully everyone can see. You can see that the left half, or this in your case would be the right half, is normal. It has the white coating. And what I had done was this is a phosphor. I had it removed from the other side so you can see the plasma inside. There we go. And so the blue, can you cut the lights? Okay. What do you know? I mean, first of all, what you notice is the blue is the plasma. And this is argon gas at less than atmospheric pressure, with a little bit of mercury. And the way a fluorescent light bulb works is that you run a current through here, and you get a current going through your gas. And when you get the current going through the gas, it becomes a plasma. The plasma gives off blue light, which you can see. It also gives off a lot of ultraviolet light, which you can't see. And the ultraviolet light is absorbed by the phosphor, the white coating here. And when it absorbs the ultraviolet, it gives off light in the visible. And it gives off a lot, and it gets very bright. And fluorescent light bulbs are much more efficient than regular incandescent light bulbs. They use much less energy. And they're all plasma-based. And all of the new innovations in lighting, for the most part, are all plasma-based as well. You can also, and if you want afterwards, can come up, and you can see if I take a magnet, it's too hard for you to see in the back, but I can actually take a magnet and move the plasma back and forth just using magnets. The other thing which is very intriguing about this is that the temperature of that plasma is more than 10,000 degrees Celsius. But obviously, I'm not burning my hand. And this is just, I mean, there's no difference between this bulb right here and the bulbs you see anywhere else in your schools, except I took the phosphor off. So with that, it means I have to ask you a question. All right, the particles in the plasma, in that bulb right there, can reach temperatures greater than 10,000 degrees Celsius. In fact, the electrons are probably closer to 20,000 degrees. But if I touch the glass, it's warm. It's warm. But it's certainly not burning my hand. It didn't melt the glass. At that temperature, glass can't withstand 20,000 degrees. So what's going on? Why doesn't the glass melt? Or why don't I burn my hand? A is that the inner wall of the glass tube absorbs most of the heat. B is that the plasma isn't touching the glass, so it can't heat it. C, there are not enough plasma particles inside the tube to heat the glass to that temperature. Or D, the white fluorescent coating is absorbing most of the heat. So take a minute, and then I'll see what you think. Okay, A, the glass doesn't melt or you don't burn your hand because the inner wall of the glass tube absorbs most of the heat. Okay. B, the plasma is not touching the glass, so you can't heat it. All right. C, there are not enough plasma particles inside the tube to heat the glass to that temperature. Okay. And D, the white fluorescent coating is absorbing most of the heat. Okay, so I'll give you a couple minutes. A neighbor who doesn't agree with you and convince them that you're right.
You would limit the number of plasma particles constant in both? Is it particles in the plasma?
No, she said. Okay. Let's see how we did. Like, why doesn't the glass melt, or why don't you burn your hand? The inner wall of the glass tube absorbs most of the heat. Nobody. I realized also I said that that couldn't be the case right before I put the question up. The plasma doesn't touch the glass, so it can't heat it. Okay? There are not enough plasma particles inside the tube to heat the glass. And the white fluorescent coating absorbs most of the heat. Yeah, if that was the case, I would have burned my hand pretty quickly. I realize I gotta be careful what I do beforehand. It's C is the correct answer. It turns out that although most of the light appears to be coming from the center, the plasma, just like a gas, fills the tube so that it does touch the inner wall of the tube. But what you do when you make a fluorescent light bulb is first you evacuate the tube of air, and then you put in just a little bit of gas and a little bit of mercury. So it turns out that there's not enough particles in there to raise the glass to that temperature. Another way to think about that is think about when you have an oven on. Let's say you put an oven and preheat it to 450 degrees. You open the door of the oven and you put your hand, don't touch anything, put your hand into the oven. It's warm, that's gas that your hand's in, but you don't burn your hand. But if you were to touch the wall, the metal, which has many more particles, then you're going to get a very bad burn. That's the same sort of idea. There aren't enough particles in there, heat capacity, how much heat they can transfer, the way they can transfer their energy to heat up the gas. And so that's why it's answer C. Okay, so now let's talk about what happens in the laboratory. Because to get a fusion reactor, you've got to heat up a plasma not to 10 or 20,000 degrees, but to 100 million degrees. How do you confine something like that? What kind of bottle, what type of reactor are you going to put that into? Well, there's three ways to confine plasma in general. First one is how the sun does it. It uses gravity, pressure and gravity. And in the center of the sun is where the fusion occurs, and it just squeezes the fuel together. The one that I spend all of my time worrying about is magnetic confinement. We use very strong magnetic fields. And it turns out that a charged particle, not a neutral one, but a positive or a negatively charged particle, will spiral around a magnetic field. And what you'll find is that they spiral in opposite directions depending upon their charge and also on their mass and how tightly that spiral is. So here's a nucleus making a wide spiral in this direction, while an electron makes a tight spiral going in this direction. The other way is to do inertial confinement, and it's also known as laser fusion. And what you do is you take a very intense laser beam and a solid pellet of your fuel, and you irradiate in all sides the pellet. What happens is that it blows off the outer, it vaporizes the outer, and that blows off very quickly and causes a compression. And so you get a tremendous amount of pressure in the center, and again, you squeeze your fuel together. Well, at PPL, Princeton Plasma Physics Laboratory, what we do is we use this idea of magnets. And the idea is that if they're going to spiral around, then why not get your magnetic fields to go in a circle, like a donut? If you can do it right, then what happens is this 100 million degree plasma just travels around in a circle and never touches the walls the outside walls, because it will vaporize the walls. And when we lose our confinement, which we do on occasion, we can vaporize part of our walls. And so it's something we have to be careful that we don't do too often. The machine we use, and there are a variety of machines, is called a tokamak. It's a Russian acronym. It means basically a donut-shaped confinement device. And they've taken different parts of the various words in Russian, put it together, and call it a tokamak. What you can see is you've got, in white here on the outside, a vacuum vessel made out of stainless steel. And you put magnets. These are big magnet coils around here and around here. Here's showing just 4 of them. These are the main magnetic fields. And you're going to try to then cause your plasma to go around in a circle. And there are other, you need not just these main magnetic fields, so you have other magnetic fields here. And one of your main heating magnets runs down the center over here. And I'll talk about the details of this in a second. So how do you go from 0 to 100 million degrees? First thing you do is you basically create the world's biggest toaster. And what we do is it's called ohmic heating, electric resistance heating. And it works the same way the toaster works, so if you're going to heat up bread. What you do is you run a huge current through the plasma. And the plasma has a resistance to that current going through, the electrical current, and that causes it to heat up. You can get to about 40 million degrees that way if you run a big enough current. The problem is that as you heat up the plasma, it conducts electricity better, the resistance goes down, so you have a harder time heating. So you can't get to 100 million degrees that way. So another way you'll try to do it is what's called neutral injection heating. Neutral because you want to be able to go through the magnetic fields, and a charged particle spirals around a magnetic field. So what you do is you take very energetic neutral atoms, so they can cross the magnetic field and enter the plasma, and then they'll give up the energy like through collisions. And so it's just like thinking if you're going to play billiards or pool, and you're going to break, and the white cue ball is going to give up its energy to the other balls through collisions. And so what you've got to do is just use an accelerator, use a particle accelerator, and send in neutral atoms. Let them give up their energy through collisions. And that'll get you pretty close, but it's still not going to get you far enough. And so the last way is we use radio waves. Basically, we use microwaves. And it's very similar to microwave cooking. We inject very high power microwaves, millions and millions of watts, into the plasma and use that to heat it up. And it's the same type of process as when you put any type of food in a microwave oven. You need to do all 3 of those together to try to reach this 100 million degree level. And here's just to give you an idea, is for the neutral beam injectors, this would be looking at the top of the donut, and you can see what we do is we've got a bunch of them around the tokamak, around the machine, and they're all coming in. We can turn them all on together. We can turn them on separately. We can change how much power goes in one or the other. And you can see that at least at TFTR, the tokamak fusion test reactor at Princeton, we can put in up to 35 million watts of power. You know, think about that for a second. Some of your radio stations say we're 50,000 watts of power coming at you. So we're looking at 35 million watts. This is a huge amount of power, huge amount of energy that we're putting into this. Then the other question is, so if that's how we heat it, how do we know what's going on? I say I've got to reach 100 million degrees. How do I know that my plasma is at 100 million degrees? We have the world's largest thermometer that we just put. No. There's a bunch of things that we do. One is we have to know how our magnetic fields, confining this 100 million degree beast is critical to our success. So we have to know how the magnetic fields are. And what we do is we take coils and we put them around the outside of the tokamak. And these coils pick up currents that are produced by the plasma. And they help us from these currents, figure out what the magnetic fields are like inside the plasma. We also have radiation and particles escaping. Light, ultraviolet light, visible light, X-rays, infrared light is coming out. Particles, for instance, the neutrons, they're not affected by the magnetic fields, they come flying out. And from that's one of the ways that we can measure is how clean is the plasma, are there any impurities? how much power that we put in gets lost by the light being radiated. We can also measure the temperature. Is one of the ways we measure the temperature. And we can find out how many fusion reactions occurred by counting the neutrons. The other thing we do is we can put into the plasma electromagnetic waves, and that, for instance, could mean a laser beam. We can put a laser beam into the plasma and look and see what happens to that laser beam as it passes through the plasma. It actually scatters off of the particles in the plasma. And that's related to their temperature, to their density. And this is the predominant way that we measure the temperature, for instance, is use a laser beam. Okay, my last question for you. Microwave oven in your kitchen cooks food because water in the food absorbs the microwave energy. In a tokamak, we use very high power microwaves to heat the plasma. That plasma consists of the isotopes of hydrogen. That's deuterium, that's tritium. It's hydrogen. Why does it work? Why do the microwaves heat the tokamak plasma? A is water is H2O. And so the isotopes of hydrogen, which are H, will also absorb the microwaves. B is that the frequency of the microwaves are tuned to the plasma frequency, while those in the oven are tuned to the water frequency. C is that the walls of the tokamak absorb microwaves, and they give off heat, and that heat is absorbed by the plasma. And D is that there's some oxygen in the tokamak, and that combines with the hydrogen to form water, and then the water can then absorb the microwave energy. So those are the four choices for your answers. I'll give you a minute. Okay, let's take a poll. A, water is H2O, so the isotopes of hydrogen absorb microwaves. Okay. B, the frequency of the microwaves is tuned to the plasma frequency, while those in a microwave oven are tuned to water. Okay. C, the walls of the tokamak absorb microwaves and give off heat. Okay. And D, there's some oxygen in the tokamak, and that combines with hydrogen to form water, and that absorbs microwaves. He's convinced. Okay, convince your dad. So find someone who doesn't agree with your answer and convince him that you're right. Okay. A, water is H2O, so the isotopes of hydrogen will also absorb the microwaves. Okay? The frequency of the microwaves are tuned to the plasma frequency the same way they're tuned to the water frequency. Okay? The walls of the tokamak absorb microwaves and then can heat the plasma. All right? And there's some oxygen in the tokamak that combines with hydrogen, forms water, and that's how it works. B. Turns out that in a microwave oven, you have a very particular frequency of microwaves there, and it's tuned to how a water molecule vibrates. And you can do the same thing. It turns out a plasma has a natural frequency, and so you want to have a resonance, and so you can choose the frequency of the microwaves. Actually, you could even choose to heat just the electrons. You could choose to just heat the ions. They have separate frequencies. And so you actually can tune your microwaves. And so it's B. Okay, so let me show you finally now what a reactor looks like, a working one. Let's see. First of all, there's a person right there. There's another person right here. You can't even see the donut. It's going around inside here. This is the one at Princeton, and this was shut down last year for political reasons, actually. This was, at one point, 10 years ago, the largest in the world. When it was shut down, it's, I think, the second largest in the world. There's one in England that's much larger than this. The neutral beam injectors that inject those neutral particles are right here. As you can see, they're very large because they're particle accelerators. And they'll send in their neutrals like this. Everything else you see is either a magnetic field coil or a way to figure out what's going on. Measure neutrons right here, or measure the light that's coming out. All these white pipes up here are cooling, water cooling. Inside looks like this. That's the inside of the donut. And that's Doug Lozier. These are graphite tiles, very similar to what is on the space shuttle, to protect the metal from the intense heat. When we lose some of the plasma, our magnetic field structure isn't good enough. You see it goes around in a circle, and right here are two of our microwave antennas right next to him. So you can see he could just about stand up in this. If you turn it on, and we can use as a reference source the two microwave antennas, I'll show it like this. You turn it on and heat up your gas to 100 million degrees. Doug gets vaporized. He's gone. You can see there's the antenna right there. Okay? And what you see is that actually in the middle, right here, there's very little light. This is a visible camera taking this. There's a lot right here at the edge. It turns out that the light from here is all X-rays. And it's only here where the plasma is very cool, relative. 100 million degrees is tens of thousands of degrees, that you get predominantly visible light. Now this particular machine every plasma only lasted about 7 seconds. And here's one of our most famous plasmas that produced the most fusion power. And I'm just showing you the center part, the first 4 seconds. And you can see for a very brief period of time, we turned all our heating on, and we went above 10 million watts of power. So we made 10 million watts of fusion power. However, we put 30 million watts of power in, heating power. So our efficiency was about a third. A reactor, you've got to go to above an efficiency of 1. You want it to produce more energy than it consumes, so you can then give that energy to various households. So a reactor, and this is just a cartoon since we don't have a reactor yet, would have a tokamak or some other fusion device here, and then would have some way to get all this energy and turn it into electricity. And one way would be to absorb the energy from the neutrons, which come flying out, let some kind of blanket. One way might be a lithium blanket. And lithium absorbs neutrons and produces tritium, so you can make your own fuel. And then you'd heat this up, and this heat would go through a heat exchanger and eventually turn a turbine, and that turbine would produce electricity over here. And so this part is the sophisticated part. We haven't gotten quite close enough to worrying about the heat exchanger and how to get the electricity out in our work. So this is still pretty crude in how we're going to get it out. Now the future of the tokamak is very uncertain right now. This is an earlier version of what's called ITER, the International Tokamak Experiment Reactor. This is a proposed experiment, a collaboration between the United States, Japan, Russia, and the Europeans to make an experimental reactor that would produce electricity. It would ignite, is what we call it. It's a tokamak, just looks like the other one I showed you, but let me show you one thing here. That's a person. Okay? It's huge. It cost $1 billion to design this. About 2 months ago, the United States decided we didn't want to take part in this anymore. Political reasons. The reason was it was too expensive. At least that's the political reason. The Russians, Russia has its own economic problems right now, so they're sort of out of it. And the Europeans and the Japanese are trying to decide what to do. Can they make one of these type of machines by themselves? Can they make also perhaps a smaller version which won't do quite as much, but will still get us close to producing electricity? Out in California, I mentioned only briefly laser fusion. California does have what's called the National Ignition Facility. It's under construction right now. This is the size of it. This is laser fusion. That's a large truck right here, just to give you an idea of the scale. And the fusion reaction occurs all the way down here. All of this is just power supplies for the lasers. This is getting funded because it has military applications. You are basically producing a small little hydrogen bomb every time you ignite one of these. And so the military, the Department of Defense, is funding this. And it also, though, has energy applications. So this is in slightly better funding positions, but has not actually had as much experimental work. At Princeton, our next experiment is, since we are not taking part in making this big one, we're going to try to make a little one, but we're going to try to be a little clever about it. This one is shaped, instead of like a donut, more like a sphere, a baseball almost, with a very thin hole going through the center. It turns out when you push your tokamak in like this, you can confine the plasma with a much smaller magnetic field. And a lot of the expense has to do with your magnets. So this is one place, and this machine right here will start experiments next spring. Some of the difficulties, though, is that this hole gets very small. You've got to put a lot of electricity through here to produce your main heating, your toaster oven heating, right through your big currents. And so you have an engineering problem there. And no one's trying to make one of these at a large scale. Just to give you a quick idea, how close are we? This is, we can have electricity. This is an efficiency of 1. Energy in equals energy out. And you can see that our experiments are just starting to skirt where our efficiency is 1. And so this will be the next area we're going to move into. And eventually we've got to get to here, where we're producing more energy per reaction. So really what it comes down to is, can we afford to do fusion research? Is it affordable? It's, in principle, an unlimited energy supply. I'll give you some numbers. We spend in the world $1.5 trillion every year on energy. The United States spends $450 billion. During the Persian Gulf War, we went to Kuwait and Iraq to protect our oil. We spent so much money, it was more than the cost of the entire US fusion program. In terms of energy, we spend less than 1% of all our energy expenditures, how much we spend on energy, on research into alternatives. Any alternatives, fusion, solar, anything you want. And on fusion, we spend just 0.05%. So we're spending very little money in this country on energy research.